Dear students, before going into the detail of this chapter, first I would like to discuss this phase equilibria of one component system. See, what is the meaning of one component here? The meaning of one component means like if we have taken water, suppose that water, so H2O is one component, and we try to study of this different phase means that solid, liquid and gas, they are technically, scientifically, they are said to be phases. Usually we are very used to say that these are the states of matter: solid, liquid and gaseous state. Okay, I'm not telling that this is incorrect, but the more appropriate word is solid, liquid and gas. These are the phases of matter. So what I'm trying to explain here in this heading, phase equilibria, I'm going to tell you what factor is controlling this phase transition, right? And phase coexistence means there are many questions we have that these phases are coexist. Can they coexist with each other or not? At some point they coexist. Coexist means solid and liquid together they exist. So here the main aim of this heading is phase transition, phase transition, phase transition, and phase phase means solid, liquid and gas. Transition means change of solid to liquid, liquid to gas, like that. So phase transition and phase coexistence. So see, phase transition first. Which factor is controlling these all these phenomena, phase transition or phase coexistence, right? So can anyone guess which thermodynamic factor? I'm giving you the hint. Which thermodynamic factor is controlling all these transitions and phase coexistence? So see, there is one physical, you can say thermodynamic parameter known as chemical potential. Chemical potential. Chemical potential. See, chemical potential is represented by mu, right? So chemical potential controls phase transition, controls phase transition, phase transition and phase equilibria, and phase equilibria. Now the big question is here, that what is chemical potential? What is chemical potential? Right? See, chemical potential, this is very, very important thermodynamic parameter. And this chemical potential is defined as mu is equal to change in Gibbs energy, change in Gibbs energy per unit change in the number of moles add constant T and P, right? In a simple words, you can say mu is nothing but this is, see, in the beginning I have told you that this chapter is the extension of thermodynamics. Because if you want, you can learn directly, okay, what is vapor pressure, what is Raoult's law, and okay, the chapter is over. But if you want to develop, I mean, understanding of the subject, then you have to follow this path. So this is bar. When we are putting bar here in thermodynamics, it means per mole. So you can write in English here, Gibbs energy per mole, per mole. So basically, chemical potential is nothing, not a new, thermodynamic parameter or thermodynamic term. For you, it may be new, but this is not new actually. This is the Gibbs energy. So if you want to calculate the chemical potential of any component in pure system or in mixture, you have to take Gibbs energy of that system, divide with the total number of moles, Gibbs energy, divide with the total number of moles, you will get the Gibbs energy per mole. Why we are dividing this? This is the purposely we have divided this with the number of moles to make it intensive. This is intensive. So what is the significance of intensive? What is the application of this intensive? Why we are making this intensive? You know why we are making this intensive? Our purpose is to make independent of independent of quantity, independent of quantity. Means you are setting a reaction or a process or a physical change, or if you have designed a phase transition with the 100 gram of water, somebody else has established his or her experiment with 10 gram of water, somebody has established his experiments with 1000 gram of water. That hardly matters, because this gives energy per mole. This is a intensive, independent of quantity, independent of subdivision of the sample. It is not additive in nature now. So it is immaterial that how much quantity. This is the reason why we are making some physical quantities intensive or extensive. So suppose that I have devised a reaction, or I have devised a physical process. Suppose that I am going to observe this vapor pressure, and I have started with 10 gram of water, and somebody else have started his experiment with 100 gram of water. Hardly matters, because we have a unique thermodynamic parameter through which we can explain the vapor pressure. So that's why here we are taking this Gibbs energy per mole to make intensive, because Gibbs energy itself, it is extensive, but when we take this per mole, then it is intensive. So basically, chemical potential controls the phase transition and phase equilibrium. Means whatsoever phase is changing, means solid is converted into liquid is converted into the vapor, solid and vapor are interconverting to each other. All thing you can explain in terms of mu, right? See, Under equilibrium condition, you can write equilibrium condition equilibrium condition right. Under equilibrium condition, see this mu is same for what, all the phases which are under equilibrium. Suppose that we you have taken a closed container, some liquid water is there, liquid water is there, right, and vapor is also there, some molecules in the vapor phase. So this is vapor and this is liquid, and both are under equilibrium. Any component, suppose that we have taken H2O, liquid, H2O, vapor. You know, whatever the temperature and pressure of this liquid is there, the same temperature and pressure of this vapor is also there. You cannot say that under equilibrium condition, this liquid has some different temperature and this vapor has some different temperature. If there is equilibrium condition, means both, see, liquid and this vapor both are at the same temperature and the same pressure. So this liquid to vapor, this is endothermic process, endothermic, and vapor to liquid, this is exothermic. Right, this phase transition. So suppose that it is this equilibrium condition is given, right? So two phases we have here, liquid and vapor. So under equilibrium condition, you can write chemical potential mu of liquid water is equal to the mu of vapor. See, so simple expression that we have, that mu of liquid. So you can say that the Gibbs energy of liquid per mole, not because you know the moles may be different here in the liquid and in the vapor. So it is always defined per mole. That's why this I mean different term chemical potential is introduced here. So under equilibrium condition, the chemical potential of liquid is equal to the chemical potential of vapor. Right? Means the Gibbs energy per mole of this liquid is equal to the Gibbs energy per mole of this vapor, right? So in this situation, and this is true for every type of phase transition, not only for water, for any kind of. Suppose that if you have taken for example, we can consider that H2O solid and H2O liquid. Again, this is solid to liquid endo and liquid to solid exo, right? Exothermic, and this is endothermic process, right? And if delta S is asked, what about delta S for this change? Delta S, or you can say S for this delta S for this transition is greater than 0. Greater than 0 when solid is converted into liquid. So liquid minus solid, entropy of liquid minus entropy of solid. So entropy of liquid is more than the entropy of solid, so delta S is greater than 0. So here you can say that if you can summarize this expression, if mu of solid at given T and P is equal to mu of liquid at given T and P, whatever T and P we have taken, if they are equal, then solid and liquid water coexist means under equilibrium, means both were exist together. Hopefully all of you are understanding this. This is totally equilibrium situation, because if you understand this properly, then you can understand when we provide heat, then this equilibrium will shift which side, because vapor pressure is defined under equilibrium condition. So first you have to understand what is the meaning of here equilibrium, right? Suppose that if mu solid at any given T and P is more than mu of liquid at T and P, then tell what will happen if solid has more chemical potential than liquid. Then solid has more chemical potential. What is the meaning of potential? Potential means ability to do something. So sometime in some writers say chemical potential is the measure of escaping tendency, so if solid has more chemical potential, means solid has more escaping tendency to convert into liquid, means more and more this solid will exist in the liquid form. Then what? Water is in liquid phase. Then water is in liquid phase. So when a matter exists in liquid phase, when a matter exists in solid phase, when a matter coexist in solid and liquid, all these things are determined and controlled by chemical potential, means Gibbs energy per mole, right? And now third situation is now clear to all of you, that if mu solid at any given t and p is less than mu of liquid, means this time this liquid has more chemical potential, more ability to convert into what this I mean solid. So this will then what we can say, the water exists, water is in solid phase, right? So hopefully all of you are clear that what a controlling factor we have, this chemical potential. This chemical potential controls each and every see here I have written uh, see here I have written endothermic, means delta H is positive here, delta H is positive here, hmm? Delta S is positive here also, delta G is there, but this is not explained, this phase transition or phase equilibrium, it is not explained in terms of entropy only, it is not explained in terms of enthalpy only, and even it is not explained in terms of Gibbs energy, because Gibbs energy is extensive, so that depends on the quantity. So you cannot make any general definition. So for general definition, you have to take either you name chemical potential or Gibbs energy per mole, right? So one very important point here, that here two variables are controlling this, that is temperature and pressure. And no, you know, these two are also known as potential of normal variables. So temperature and pressure, they are very important. So one thing is clear, that which thermodynamic parameter is sufficient, alone sufficient to explain the phase transition and existence of any matter in solid or liquid or gas, that is the chemical potential, right? And you know, this chemical potential depends on the temperature and pressure, and all of you are knowing that one equation we have, that is delta del G is equal to minus S dt plus V dt. So all of you are familiar with this equation. It definitely was taught in the thermodynamics. This is very important equation. So you can write here. See, means on differentiation of this equation, we can write del G by del T, del G by del T at constant P, at constant P. So if you take in constant P, so dP is equal to 0. So you can write here minus of S and take it per mole. So this is this. So you can write, or you can write, when you have taken per mole of this, so this is what, del mu by del T, del mu by del T at constant P is equal to minus of S, right? So this is equation 2. Similarly, you can write del G by del P at constant T is equal to V, or per mole if you want to write, so del G per mole by del P at constant T, this is equal to V bar. Or you can write here, or and this is equation 3. So these are the equations through which you can explain the dependency of chemical potential with temperatures, and chemical potential, variation of chemical potential with pressure. So usually for such type of phase transitions we take pressure constant. So temperature, with temperature you can explain this, right? Now if you further consider this equation 2, so and if you want to make a plot between chemical potential and temperature, so you know this is a derivative, you can say. So the ratio of this will the slope and this negative slope is here. So if we take mu here and T, so between mu and T, what which type of plot we may get? This type of plot, and negative slope, negative slope. So if you see here this equation, which equation means taken here, del mu by del T at constant P is equal to minus of S. So if you consider this equation, the variation of mu and T at constant P means P is constant. So the negative slope is what? The entropy change. And all of you are knowing that the entropy, molar entropy of gas is more than the molar entropy of liquid and molar entropy of solid. Molar entropy of solid. So if we try to express all these three phases on the same graph, so for which phase you are getting the steep slope, more negative, obviously for gas, you know, from the third law of thermodynamics, you know this S is greater than 0 for every matter, for every substance above 0 Kelvin. So we are here studying at above 0 Kelvin, much higher temperature than 0 Kelvin. So this is always positive. So this is always positive. So you can say that this is always negative. So slope is always negative here. It is what justifies, because slope, why always this negative slope? Because this s is I mean per mole, s is always greater than 0 as per third law of thermodynamics. As per third law, right, of thermodynamics. So since it is greater than 0, entropy change is greater than 0, or absolute entropy is greater than 0, so you can say that we always get this del mu by del T at constant P is less than 0. So you can say that okay, this slope is always negative. So this is negative slope. Now see here, for all this solid, liquid and gas, entropy change in this order. So I mean entropy of gas is much larger than this. So if you plot a graph between mu and T for different phases, what a beautiful graph you may get from here. See, I'm not plotting this graph exactly scaled graph, but this is what unscaled graph. So for which phase we are getting uh, uh, less slope. So for solid, because you know this change is very less even at same temperature and pressure. So we get this type of for solid. This is for solid. Now see, for liquid, we get like a graph like this. This is for liquid, and for gas we will get the most uh, steep slope like this, right? So this is a little bit mm, liquid, and this is for gas, right? So solid, liquid and gas, and you know what, this intersection P is constant, right? P is constant. So P constant. See, very interesting thing we are getting here. See, this is a liquid and gas intersection. This is liquid and gas intersection. This is a liquid and solid intersection. And see, this is a gas and solid intersection. So this is very interesting. Result we may conclude here. See, whatsoever this intersection is, this is the boiling point. TV. And this is the solid liquid, so this is a melting or freezing point, right? See, this is the melting or freezing point, and this is the boiling point, right? And if you see here, so you will find that this enclosed region, this is the liquid phase of the, I mean, if you want, you can take water. So this is the liquid phase. So and see, under the extreme condition of this temperature, if you see move this direction, so you will get what, see, gaseous phase. After this, see, this is the I mean boiling point situation. After that you will get gaseous. Under this extreme condition, low temperature region, you will get what, solid. And see, this solid line you are getting. So this enclosed region is represents the liquid phase. So if it is asked that tell which phase of the matter is the restricted phase, so every time you have to say liquid phase is the restricted phase of matter, because under extreme conditions of temperature and pressure, you will get either solid or gas. So this you can justify with the help of this graph between plot between mu gives energy per mole, or molar gives energy, and temperature, right? So the restricted phase of matter is liquid phase. The restricted phase of matter is the liquid phase. So save the water and save the life, right? Because it is the restricted phase. Once the extreme weather conditions will come, definitely you will get what, water as a liquid phase or as a solid phase, right? So intersection of this solid liquid line at this point, suppose that this is what, point A, and this intersection point is B, and there is one more intersection point, this is what, gas and solid, this also exists here. So you can write here that at this point A, you can write mu of solid uh, and Tm means this temperature, melting temperature, Tm, and P is constant, so Tm is equal to mu of liquid Tm, right? So at this point you can write this. Similarly at point B you can write mu of liquid Tb boiling temperature, this is equal to mu of vapor Tb. So at this point the chemical potentials are equal. Right? So at this point solid liquid coexist. This point A, solid liquid coexist, and at this point liquid vapor coexist, right? So this is all about the controlling factor of phase. Which thermodynamic factor is controlling the phase? The answer is chemical potential. The answer is chemical potential, right? So if we plot phase of any matter as a function of temperature and pressure in these two variables, in terms of these two variables, the whole diagram what we are getting, that is known as phase diagram. And definitely I would like to explain the phase diagram of water here, so that you can understand, and it is very important to understand the further concept of this chapter when you go through elevation in boiling point, depression in freezing point, all those things you can very easily understand, right? So phase properties. So what is phase diagram? Phase diagram basically, phase diagram describes the properties of phases in terms of state variables. Basically we are taking here T and P. So in terms of T and P, we can define the properties of phases. See, I have for you this one figure to describe the phase diagram. See, this is a very important and very simple plot I have taken for you people. This is called phase diagram. See, this is pressure and this is temperature. And see what this line represents. The line represents the interface. In this region you have liquid phase, in this region you have solid phase, and this is gaseous phase, right? See, this is called triple point. At this point, liquid, solid and gases, all three coexist. So one by one we can define all these things. So see, suppose that this point is O. This point is O. Here we can take any point A, and this is C, and this is what, B. So OA line represents OA. This represents solid liquid interface. Interface is the hypothetical contact phases, means hypothetical plane, you can say, at which both the phases are in the contact. And OB is the solid gas interface. Solid gas interface. And OC line is the liquid gas interface. Liquid and gas interface. Right? See, point O is called triple point. O is called triple point. And you know, for water, what is the triple point? For water, if you take for water, so this is a unique point. It is 273.16 Kelvin. Temperature is 273.16 Kelvin. And pressure is what? Point P is 0.0006 bar. And temperature is 273.16 Kelvin. So this is called triple point. At this triple point, what we can say, that mu of solid T and P, this T and P, is equal to mu of liquid T and P is equal to the mu of gas or vapor at T and P. Means all three phases coexist. Right? All three phases coexist. So the degree of freedom is 0 at this point, and degree of freedom 0 means no variable is required to define this state. This is a unique point of any phase transition. So triple point, this point is different for different matter. Means triple point means temperature and pressure. This temperature, so, and for every matter this point is different. See, this point C is called here critical point. Point C is called critical point. Critical point. You know, at this critical point, all of you have gone through this critical temperature. So don't think that only gases have this critical temperature or critical phenomena. See, gas and liquid equilibrium, they are defined at this. So critical point is the point at which the density of liquid is equal to the density of vapor. Means liquid and vapor phase merge together. Liquid and vapor phase, vapor phase merge merge together. Means you cannot distinguish liquid from vapor. Means you can say only one phase of matter exists, right? So this is the, I mean, unique point for every matter. After this, see, that's why in the phase diagram, no, I mean, see here, this line has still arrow is shown here. This is also arrow shown here. Means you may get further more and more, I mean, lower value. You may get a more and more higher value, but here you cannot have any other value. So that's why in the phase diagram, if this type of see dot is given, then you easily understood, okay, after that see, liquid and gas phase merge together and whole matter exists in the vapor phase, right? But see, this line is still what moving, means still there is possibility, right? So this is the phase diagram, this is the phase diagram. Suppose that if we I mean put some I mean again I am taking the same graph to explain you, uh, but this time I'm making this graph by own, because I'm trying this time phase diagram of water. This is very important and all of you should know. Phase diagram of water. So this is one of the important point. And okay, but before going in detail, one thing also I would like to mention here, that see, this OA line is moving away from the y-axis, from this axis, see, like this little bit here. So there are three possibilities that this OA line, this is y-axis, and this is x-axis. There are three possibilities that uh, this line move parallel to y-axis. This is one possibility. Other possibility is this is moving like this, not exactly steep like this, but okay, qualitatively you can understood. And one possibility is this, right? And So although they are not steep like this, but there is some meaning I want to explain you. This is O, what I have taken here, OA, okay, OA, OA dash, OA double dash, right? So all have, some meaning here. This is P and this is T. If OA line is parallel to y-axis, means the density of this solid and liquid, the density of solid and liquid is almost equal, right? If OA line is like OA dash, which is away from y-axis. This has also some very important meaning, that the density of solid is more than the density of liquid. And this is the normal phenomena for every metal, because in most of the compounds you will find that this density of solid is more than the density of liquid. And if this line is OA dash double dash, like towards y-axis, then it means what? Density of solid is less than the density of liquid, and this exists for water. Remember this. So for water, this line solid liquid, you can say solid liquid interface, this is this line is interface is tilting towards y-axis, and it has this meaning. So water, and one more element, I think bismuth is also showing the same property. So this is very important meaning of this movement of this graph, density related to the density. So water is exceptional. The behavior of water is exceptional. Because normal behavior is this. This is normal. Normal feature is this. This is exceptional behavior, right? So and in this chapter we will focus mainly on the phase diagram of water, not for any other matter. And it is very important to you, and after that you can explain how this boiling point increases, how freezing point increases or decreases, like that you can very easily explain, right?